continue with the last talk today in this afternoon session. So the speaker is Anton Souslov. He's here in Cambridge, and he'll tell us about odd active solids. So please take it away.
Great. Thank you very much for the introduction and for the opportunity to speak here. I'm in Cambridge, but not quite here. Here, about 5 minutes down the road in the Department of Physics, which we call the Cavendish Lab. And what I would like to tell you about are active solids, which I hope to convince you are different than active fluids. And in particular, in terms of the theme of this workshop on anti-diffusion, I hope to convince you that pattern formation in active solids is also different than anti-diffusion pattern formation in some fundamental ways. Before I begin, since we've heard so much about we've heard so much about active fluids already, I wanted to introduce you the topic of this talk, which is active solids, and I want to introduce you through some examples to what I mean. So we know about pattern formation in active fluids and the fact that active fluids can perform work on their environment. The same holds true with active solids. And sort of the kind of examples that I would like you to think about are, for example, this self-folding origami, which is, has active components due to these actuators that bend a flat sheet into some particular shape. This is an example of a programmable material, right? One that exhibits its function due to a sort of pre-designed program, but there's lots of emergent phenomena in active solids as well. And so, for example, some recent experiments from Olivier Dauchot's lab in Paris show this example of a collective dynamics that happen for self-propelled particles that are individually caged in these little disks. So the ellipsoids here are the self-propelled robots. They're about 1 centimeter in size, and they go around in this larger cage, but then they also talk to their neighbors through these elastic filaments. And what you see is that through the elastic interactions, you get this interesting collective dynamics where the robots synchronize their motion. And so one common theme in active matter is that it applies across both synthetic and biological materials, and that's also true in active solids. So for example, in this more recent work on a bacterial biofilm, what you see is the same kind of synchronization of motion for bacteria that's now confined in a polymer matrix. So instead of these elastic filaments, you have an elastic polymer network that the bacteria push on and use that to synchronize their motion. And finally, let me give you another biological example that's closer to what I want to tell you about, which is this crystal of starfish embryos. So in this crystalline solid, what you see is that every atom, every particle here is a biological, sort of self-rotating particle. The reason that these starfish embryos rotate is that they use that to swim, right? Their natural swimming stroke is chiral, but here they're stuck on an interface, so they can't swim anywhere, so the only motion they perform is to swim around their, to rotate around their center. So one question you can ask about active solids is sort of what kind of elastic response will such a crystal have, and how might that be different from equilibrium crystals, equilibrium elasticity. And the interesting thing about that is there are now quite a few experimental systems that all show the same kind of active elastic response, which we call odd elasticity. And they're all based on some of the same fundamental physical principles. I'll sort of emphasize the non-reciprocity of the interactions in these systems. And in the starfish embryos, as well as in this colloidal rotating colloids experiment, these non-reciprocal interactions come from the vortices that rotating particles create in a fluid around them. So when you have, for example, this rotating colloidal system, you can see that it's much larger in terms of the number of particles than the starfish embryos. The colloids themselves are much smaller, so now the particles are about a micron in size. They're not biological in any way, they're purely synthetic, but these are magnetized colloids, and so what they do in this experiment is to put them in a magnetic field that's in plane, and then rotate the magnetic field in such a way that all of the particles individually follow it, right? And so they rotate around their axis. And so what happens in terms of the interactions between these particles is that a rotating colloid here creates a vortex around it, which creates a flow that this particle feels, and this flow will be transverse to their direction of separation. Such a force law, where the force transverse to the direction of separation, contradicts or violates Newton's third law of equal and opposite action and reaction, and we call that type of interaction non-reciprocal. So it turns out that generically rotating particles in a fluid have this interaction, but that's not a necessary condition, right? You could have other types of interactions that are also non-reciprocal that don't involve any rotations. And sort of to demonstrate that, I want to give this example, which I'll return to again in my talk, which is an example of robots that have been programmed in to interact non-reciprocally with their neighbors. Right? So I'll go into some more detail about the microscopic interactions later, but I would like to point out that the same type of odd elasticity that the starfish embryos and the colloids exhibit is also exhibited by this robotic system, with the significant difference that, again, I'll come back to, that the robots are much larger, right? They're on the centimeter scale, and therefore inertia is important in this system in a way that it's not important for colloids or starfish embryos. There's lots of other examples of this odd elasticity that involves different kinds of systems, both synthetic and biological. So what is this odd elasticity, active elasticity that I want to tell you about? Well, to begin with, I wanted to kind of reintroduce passive elasticity in this perhaps somewhat unusual notation. Right? So in this matrix equation, what you have are two vectors that represent stress and strain here. And the proportionality matrix between these two vectors, that's your elastic tensor. And in this case, where you have a passive elastic theory, there are only two components for an isotropic two-dimensional solid that are allowed in this elastic tensor. One is the bulk modulus here. That's the inverse compressibility, and it's common to both fluids and solids. It corresponds to a pressure, so an isotropic stress, that comes about due to dilational strain here. And then the other modulus, this is the shear modulus, that's unique to solids. It corresponds to a shape restoring response, right? And it tells you that if you shear the solid in one direction, it will exert a stress in the same direction. So it's a diagonal, it's on the diagonal here, and the same for both directions of shear due to isotropy. And particularly the other components here are the torque and the rotation of the particles, and these components are crossed out because you don't expect rigid body rotations to create any stresses. You don't expect any torques in an equilibrium solid. So now what's different in active elasticity? Well, I'll take a sort of simplified model here, and I'll assume that this assumption that rigid body rotations do not create stresses still holds for the solids that we consider. That's true in all of the examples I've given so far. And then this column still has to be 0, but there, if you relax the assumption of energy conservation or being in equilibrium, you still find 2 extra components of this elastic tensor that correspond to an antisymmetric elastic response in an isotropic material. So what do these components mean? What sort of phenomena do they correspond to? Well, that'll be the theme of my talk. But to begin with, to give you some intuition, how I like to think about this K0 component, this K0 odd elastic constant, is a non-reciprocal interaction between the 2 directions of shear. What I mean is that if you shear the material in the horizontal direction, this odd elastic constant will tell you about a stress at 45 degrees. But if you then apply a shear strain at 45 degrees, you'll get a stress back along the horizontal with a negative sign. Right? This anti-symmetry of the elastic tensor gives you this negative sign, and that corresponds to a non-reciprocal interactions that ultimately comes about from non-reciprocal interactions at the microscopic scale. Right, so what does that mean in terms of the phenomena you observe in these solids? Well, perhaps the kind of most obvious dynamical phenomena you will get is that if you look at an overdamped solid, right, ignoring inertia, but including a friction constant here for your displacement field, you will get a force law like this, which is first order in time, with the gradients of the elastic stress here. And it turns out that this force law with this antisymmetric elastic tensor will have a solution that corresponds to propagating waves even in this overdamped limit. Right? This is surprising because in passive elasticity we expect any sort of strain or displacement field that you induce to relax without any propagating waves in the overdamped regime. So where does it come from? Well, you can think about a sort of work cycle being created by these waves where this odd elasticity constantly injects energy into the system. This energy is immediately lost due to this friction or dissipation in the overdamped regime, but the balance between energy injection and dissipation results in these propagating waves. So these cycles corresponding to the waves can self-sustain and the waves can propagate. So we can make this, in fact, a little bit more quantitative by balancing the power injected due to odd elasticity against the power dissipated due to this frictional coefficient. If you balance these two, you get the dispersion relation for these odd elastic waves, which is different than inertial waves in passive solids, right? Where here you have a dispersion that's quadratic in the wave number and proportional to your odd elastic modulus. The reason this is interesting is because that lets you measure the odd elastic coefficient, and this is experimentally how one way that odd elasticity has been measured. In particular, this is experimental data from the starfish embryo system, where you see the propagation of these overdamped waves. The scale bar tells you that this system is overdamped. Nevertheless, the waves are long-lived, and the odd elastic modulus as measured in this system was about 7 times larger than the passive shear modulus here. So this is another evidence that this is a very active solid. Any questions so far? Yes, please.
So if I step back a bit at the micro scale, so I should be looking for torque coupling, and I should be looking for specifically what sort of couplings to generate.
Yeah. So there's now lots of examples of the microscopic interactions. I think this ingredient that the action-reaction asymmetry somehow broken is maybe the most general one that I can apply. But a dependence of somehow of torque on strain is maybe another, equally broad example.
But I had a general question, right? If you still say it's written as a divergence of a stress, when the stress is a function of modulus, shouldn't it mean it's divergence or something? Meaning you need to be force balance. So that's what gives there.
So I would say that, that you do get, there is a kind of conservation law that that this sort of equation assumes the fact that you have a divergence of a stress, and that's the fact that no linear momentum is generated by this autoelasticity. You only have kind of linear momentum dipoles rather than linear momentum monopoles, if you wish. So that's, that's an assumption that's not always valid for active solids right there. But it will be valid if you don't have a substrate to couple to sink or source your linear momentum from. Yes?
So you say it's either dumped in the fluid or it comes
So you still have the fluid to dissipate energy, but you don't have sort of, let's say, in these models, you don't have self-propelled particles, say, which would be sort of let's chat about it a little bit.
In the starfish embryos, so why are the interactions non-reciprocal?
So it's the same reason as kind of in the colloids, because each individual embryo rotates and they all rotate in the same way. If you think about the dependence the direction of force on each embryo in a pairwise interaction, right, it will be transverse to the axis of separation, right, and that's not consistent with Newton's third law.
So I mean that's transverse, but why is it non-reciprocal? Why, in what sense is starfish A doing something different to starfish B than starfish B to starfish A?
I would say, okay, so that again, my sort of definition of non-reciprocal is really that that you break Newton's third law of action and reaction, right? And I think so generating a net torque does that, right? Whether that in what way your forces, right, being transverse means that I guess your direction of force on this particle, right, is opposite to the direction on this particle, and so that's another kind of way of saying it. They're sort of different in their interaction. So let me give you some more maybe examples of ways of realizing these odd solids, which I think are maybe more explicitly non-reciprocal and maybe don't kind of question what is the boundary between reciprocal and non-reciprocal. And the way that, the next kind of example of phenomena that I want to give you for odd elasticity has to do with elastostatic response. And so what I want to talk about is an elastostatic response that's sort of similar to a Poisson ratio, but different, and has to be zero in equilibrium solids. Right? So Poisson ratio, if you remember, is the transverse response due to a uniaxial stress, right? And a negative Poisson ratio in particular means that the material, if you compress it in one direction, also compresses in the transverse direction. An odd ratio that, as we define, doesn't exist in a passive material and instead corresponds to a tilt of the material in response to a uniaxial stress. The reason that it happens is due to this coupling between the two different directions of shear that you get from odd elasticity. So this is sort of a decomposition of this coupling that says that if you have a uniaxial strain on the material, you can decompose that into an overall isotropic strain and a shear here. The odd elasticity then gives you a stress or force on the boundary that's transverse to this shear, which will only be stabilized in the static limit by having a shear strain at 45 degrees. And so indeed you see that in examples of odd elastic solids. So this is another robotic implementation. I'll give you sort of the microscopic details in a second, but first I want to point out that you do see this tilt in the overall response of the solid due to the active forces on the motors. In particular, you see this kind of tilting to the right in this video. The way that odd elasticity is sort of implemented here, that's maybe more kind of explicitly non-reciprocal, is the fact that your robot here measures the angle and then communicates this angle only to its neighbor to the right or clockwise in this example. This is sort of denoted schematically here by an arrow from this bond angle to this bond angle. And what this means is that the interactions between the two angles now, or between these two motors that are torque actuators, is non-reciprocal, right? So motor 1 interacts with motor 2 in a different way than 2 interacts with 1. And this is also sufficient for odd elastic response on the macro scale. However, this kind of simple model and robotic implementation also allow us to play around with these different force laws and the magnitude of the odd elastic response. And so I want to tell you about some surprises that we've uncovered when trying to kind of build and design these materials. In particular, kind of the way that you can now measure this odd elasticities through this odd ratio, right, this overall tilt due to uniaxial stress, and I'm going to use that as the metric, and then we have sort of in the model or in the design parameters sort of 3 different microscopic parameters. So sort of nearest neighbor spring constant, the torsional spring on each angle, and then this active non-reciprocal torsional spring. And so, of course, for such a simple model, you can calculate analytically the odd elastic response as a function of all the parameter values and see how it varies. And perhaps not surprisingly, this then agrees with the experiments, right, even up to the prefactors. What we did find surprising here is the fact that in a passive solid, when you change the constituents, the microscopic relations, or when you make the stiffness of each spring larger, it means that you will increase your elastic response. Right? There's no way to make a solid weaker by strengthening some of its components. In odd elasticity, that turns out to not be the case. This intuition does not hold. And so what happens instead, if you look at, so first of all, you can, of course, calculate this full odd elastic response, but where the surprise lies is that if you look at the response of this odd elasticity as a function of the active interactions, it starts out being roughly linear, but then becomes nonlinear, and eventually saturates at a maximum, and then decreases as you make the solid more and more active. So somehow you're injecting more and more energy into this solid, but the odd elastic response is weaker and weaker. Right? So where does that come from? Right? How can we understand that? Well, one thing we can do is to make simulations of this response, right, and see how it looks like on the microscale. And what's happening here is that you see that for small activity, you have pretty much the same elastic response in the passive hexagons here as in the active hexagons. So there's an overall tilt. It's very small, but it increases in this regime with the active elasticity. Then when it starts to saturate, what happens is that the response becomes non-affine. In particular, I mean non-affine between the active hexagons here, the ones that have non-reciprocal interactions, and the purely passive ones, right? So this is somewhere near the maximum of this odd response, where you still see a strong overall tilt to the material. And then finally, if you go to very large activity, what happens is you go back to a purely uniaxial response. And the reason for that, you could see in the video, is that the active force actually completely overwhelms the passive spring constants here. And so because your active hexagons do not deform in this limit, you do not get an active contribution to the overall elastic strength. So unlike a passive material, here you can change an active spring constant and decrease your overall odd elastic response. So this, of course, was important for us because we wanted to design things with a large active response and knowing how the geometry of the lattice interacts with the macroscopic response is one of the important ingredients. Right, any questions about this part? And so the last story that I wanted to tell you about now has to do with again, the dynamics of these materials, but now going into the inertial regime. And I'll introduce yet another model of an odd elastic solid that again breaks this sort of reciprocity. And in this model, what you have is the interaction between three different linear actuators here. You can think of them as active springs, where again, this active spring 1 talks to active spring 2, but not vice versa, right? So you have a sensor that measures the length of this active bond, communicates it to actuator 2, and actuator 2 has a force law that's determined by the spring length here. In the inertial case, the interesting thing that happens here is the fact that you have this linear instability at the level of each individual cell. And the reason this comes about is because when you start changing this spring length, you will communicate to this component, which will exert a force. This will change this spring length, induce a force here. Then this spring length change will induce the force here, and so on to drive the instability. And this instability saturates due to a nonlinear components of both the active and the passive elasticity here that drive you towards a limit cycle in the dynamics of this material. And in this limit cycle that you can see map out here, what happens is that each hexagon sort of performs an orbit in shear space going between this and this configuration. So in terms of this video that I showed you earlier, one way to interpret it is that in the beginning, each of the robot performs its own limit cycle. You can see that here. But eventually, the elastic interactions between the different active components drive it into a collective state, an emergent state, where all of these limit cycles are synchronized. And you wanted to understand why this happens, but also how it happens in terms of the dynamics of these materials, especially if you look at ever larger systems. So this is a slightly larger experimental system where I now the experimentalists have color-coded the deformations here to help track what is going on. And the way that these deformations are color-coded is by the direction of the deformation of each hexagon. So if it's squeezed in the horizontal direction, it's sort of bluish. If it's squeezed in the vertical direction, it's greenish, and so on. And you see this sort of dynamics in the movie here, where first you get a disordered pattern of color that then becomes homogenized. Right? And at even larger scales, we can't do that experimentally. But we can do that in simulations. And in simulations, we see these patches of color kind of slowly increasing in size towards the, a length scale that's comparable to the sample, it's sort of material length scale. So one way to try to understand the system is to sort of map out this color field and note that you have these singularities in it. These singularities sort of look like topological defects, although I wouldn't call them topological defects of the crystal, in the sense that the crystal is always perfectly hexagonal. What happens instead is that there are some points where the deformation field is 0, and therefore the phase of the deformation is not well defined. And as the system coarsens, you go from lots of these points to a few as they're expelled through the material. The way I want to kind of understand this instead is to go back to kind of the pattern formation language, right? And to think about what kind of pattern these active solids form and how that might be classified between these, three classic types of pattern forming systems. So to do that, we can first look at the linear instabilities in the system, right, by including now inertia as well as this overall stress tensor in the solid. This overall stress tensor will have a viscous response, an elastic response, and odd elasticity. And if you map this out, you look at the linear growth rate as a function of wave vector, you get this sort of linear dispersion relation, where both the range of length scales and the growth rates are given by this active modulus. What you see here is that this unstable branch hits 0, right, as the wavelength goes to infinity. And so these materials kind of naturally fall into this type 2 class of pattern formation. But, and this is, of course, this sort of anti-diffusive regime where you get a q² growth rate of your instability at small q. However, you notice here, what's different is the fact that at small q, you don't get a squared dispersion relation, you get instead a linear dispersion relation. And this is because of the inherent symmetries of this active solid. Usually when we write out a pattern-forming system, a reaction diffusion type, we assume the lack of inertia and chiral symmetry in the material. But breaking both of these symmetries, what happens is that you get a linear dispersion from inertia, from inertial waves, and the chirality lets you break the q going to minus q symmetry. And in this regime, the unstable branch has a linear dispersion, so it's sort of a subtype or an unusual type of type 2 pattern forming system. Of course, if we want to think about pattern formation, we have to go beyond this linear stability picture. And then we want to add a nonlinear term here. You can add a variety of nonlinear terms. Perhaps the simplest one is to have a stress that's cubic in the strain. This respects both momentum conservation in the sense that it's still under the divergence, and it respects rotational isometry.
Just a question.
Yeah.
Even within linear elasticity, the fully rotation invariant strain is nonlinear in the displacement fields.
Yeah, yeah.
Is that already taken into account in what you're talking about? So even without invoking a phenomenological nonlinear stress versus strain.
So let's.
Nonlinear strain tensor would introduce nonlinearities in the equation of displacement fields. Is that in there already, or?
So I think that not in. I think it's not in this particular version of this thing. It's of course in the ball and spring model, for example, that we have. Right?
Anton, now you don't have any friction, and you presumably now have angular momentum conservation as well. But if you have angular momentum conservation, your A has to be 0 as well.
Yeah, so that's a good question. It turns out that the A does change the, quantitatively changes the picture a little bit. Qualitatively, everything I talk about would be the same if we included the A. It's true that this particular, relation where, for example, this range of length scales is only proportional to K naught and doesn't have an A in it, would change, for example, if A were
It cannot be there if the system has angular momentum conservation.
Yeah, and it's not in this sort of simplified model, though. Again, that's just for simplicity, not because somehow A changes this picture. They are complex. This is just the real part of the growth rate. There is also traveling waves because we have a combination of sort of elasticity and inertia that sort of naturally leads to elastic. Yeah, it's still these are the I guess the imaginary part of the growth rate or the real part of the frequency will also have a linear dispersion here.
So can you say a bit more about where the linear term in Q comes from?
Oh yeah, well.
At the technical level, I mean.
Yeah.
Because that's quite unusual.
It is unusual, and I think that's something I would like to emphasize. Indeed, so the sort of two basic ingredients that we think as sort of the most general picture here is the fact that you break the Q going to minus Q symmetry, right? That's of course, and you do that because you have the sense of chirality, right? So for example, in these sort of three active bonds I showed you, right? You have a particular clockwise interaction, and if I made it anti-clockwise, it would change the system. I would, in fact, have the opposite sign of this elastic modulus.
I reckon I understand this at the level of works. That if I have a single gradient, I would pick up IQ. Where does the second I come from?
So it comes from the fact that you have 2 degrees of freedom. So if you look at the kind of matrix equation, it comes from the fact that you have 2 degrees of freedom, right? So let's say go to this here. So you have the antisymmetric part here means that you pick up, I guess, one sign between this stress and this stress. If you wanted to reduce it to one equation, right, going from this stress to this strain, you would pick up K naught here and minus K naught here, and that gives you. Yeah. Other questions? So if you plug that into the PDE, what you find is all of the same phenomenology, right, that you see in 2D. Here I've plotted it in 1D to sort of show it in a bit of a simpler way. So what you see is this linear growth rate of the instability with a particular wave number, right, that then sort of saturates or slows down in its growth. And then after some point, what you see is the coarsening of these waves to larger and larger length scales. And in fact, because we have momentum conservation and for very general choice of nonlinearity, which is why I didn't really emphasize the choice of nonlinearity here, the system will always have these waves grow towards the system size. So it's plotted here just to show are the 2 shear deformations for this strip geometry of hexagons where you see them sort of out of phase in a way that's sort of predicted by this odd elastic coupling. So the way that you have this coarsening, happens in the system is through a phase slip instability. So you have these traveling waves. Now this is just one of the shear directions plotted here. And what you see is that as the wave amplitude grows, one of the, in this sort of short video, one particular wave front is lost, and you go to a smaller Q or larger wavelengths in the system. So this kind of generic analysis lets us kind of conclude that based on symmetries and conservation laws, we expect both pattern formation and coarsening to system size in a variety of these microscopic systems, as long as we have inertia and odd elasticity together. One thing you can kind of do to break this picture is to break momentum conservation in this equation. In other words, to introduce a friction term, a friction with a substrate. And in that case, you pick up, for small frictions with a substrate, a length scale that will then cut off this coarsening at some size. We can also perform some analytical calculations to get the sort of coarsening exponent and how it depends on your on the system that you choose. In particular, here for this 1D strip geometry, you can kind of track down the coarsening. So here, what's plotted is the mode that's winning at any given time is plotted in sort of at the top, right? This is the mode amplitude for a given mode in K. And what you see is these phase slip instabilities as you go up to smaller wave vector. So from higher mode number to lower mode number. And the maximum of this mode amplitude scales as the 1 over the square root of time, or in other words, the length scale in your system goes as the square root of time, which is a direct consequence of this linear dispersion that we had in the growth rate. So I'm going to, yeah?
How is square root of t growth a direct consequence of linear dispersion?
Yeah, so I don't have a very intuitive argument for this yet. It comes about from sort of the analysis of these equations, and there's a what we do is to look at sort of secondary instability once we have a particular wave, once we assume a particular wavelength here, and from that you could get a particular power law in time.
Because in a different odd problem, the one of the drifting lattices, there also you have a linearly growing instability with linear growth rate linear wave number. And there the coarsening is super slow.
Yeah.
So it's something different.
Yeah, it is something different. I'm not, there are several of the details here that are also different, and so I'm not exactly sure. They don't exactly map onto each other. So I'm going to conclude here, but first I wanted to sort of tell you about why I think this is interesting. In particular, these materials, these systems can be thought of as, well, either active solids or robotic swarms, right? As such, they exhibit functionality that's sort of greater than the sum of their parts. So for example, this pattern, right, when you put it in a solid on a frictional surface, will drive the solid to locomote. This locomotion will then depend on things like the shape of the solid that you start with. So for example, if you pick a rectangle instead of a disk, you'll get a crawling-like motion rather than a rolling-like motion. And the presence of all of these patterns and deformations as well as these sort of basic physical principles that rely on symmetry, lets you design then materials that perform functionality in this distributed and robust way. So I'll conclude here. I'll thank our experimental collaborators in the Coulet lab, as well as the people who've worked with me on this, Jack Binish and Hito Bardink. And I hope to have convinced you that active solids have lots of interesting elastic phenomena. So thank you very much.
More questions for Anton?
Yeah, Christina, please.
So what you call the static order response, that can also occur, which I guess was, for instance, that if you do uniaxial compression, you tilt or get spontaneous shear, right? That can also occur just as a result of geometric frustration. For instance, in the Voronoi model, the silica was described with a regular length. But you wouldn't get the dynamical phenomenon there? The dynamical.
Yeah, it's a good question. So I guess, for the dynamical phenomena, well, I'll say, for the dynamical phenomena, I guess it's, more important somehow that you have this 2 degrees of freedom that are non-reciprocally coupled. I don't know if any way of non-reciprocally coupled or anti-symmetrically coupled, right?
Okay, I mean, in that case, I guess it's really the under constrained nature of the model that gives you this kind of behavior. I mean, in the case I mentioned.
Yeah. So I think.
I don't know if you could actually formulate it.
Yeah, so that's a good question. Yeah, in the static response, so another kind of very, maybe a little bit of a trivial way of getting this tilt is, of course, to have an isotropy, right? And so here we know that it is isotropic, but if you had an anisotropic material, you could have it tilt under uniaxial deformation. For us, this is more of a metric, I guess, of autoelasticity, knowing that we already have it. But in other systems, the dynamical phenomena associated would be different.
I think in the vertex model case, I mean, it would tilt, but there is a symmetry. It would tilt the other way around.
Yeah. So that's maybe another distinction.
That's more like a custom mathematical situation.
But just to be clear, I wasn't talking about isotropy. I was talking about the fact that if you have a polygon and the only constraint area perimeter, if you compress it, you're not constraining the shape. So
Here we are, we do have hexagons, but we also have enough kind of passive constraints, right? Constraints on the angles to make it, truly rigid even in the passive case. So I think that's maybe a distinct class of tilting things. But I wouldn't, I also say that I agree with you that I wouldn't kind of diagnose whether something is an odd elastic solid simply because it tilts, because there's lots of other ways to making things tilt. On the other hand, if you know that the tilt is due to odd elasticity, then it's just sort of a useful way to measure it experimentally, right? Theoretically, we can measure it in lots of other ways.
Other questions? I actually have one.
Yeah.
What happens with the nonlinear mechanical response? Are there any surprises there?
Oh yeah, good question. We haven't looked at it very much, in part because it's, in detail, it's actually fairly difficult to model. For example, we don't have an analytical expression for what we'd expect, but there may be interesting surprises. I think it's not been so well studied.
Any final question for Anton? All right, then let's thank him.